Turgeon here, bringing you physics from afar. We've got a couple of long overdue solutions for the perseverance problems. Here is the work of a previous student solving the circular motion perseverance problem. It's going to be a little bit hard to follow, but I'll give you the basic idea. The key was realizing that as this thing descended, and you can pause it and check this out. Here's the original problem. But as this thing descended the spiral, you can sort of think of unraveling that spiral and think of it as an inclined plane. And that thing is going to gain speed along the inclined plane. And here's the key. As it gains speed on the inclined plane, it now has a centripetal force. And as it gains more and more speed, it has more and more centripetal force. And the numbers came out a little weird because as I designed this problem, I figured out that the increasing speed because of the v squared was having a dramatic effect. So this ended up being a very, very small angle because that angle and the increasing speed was having such a huge effect on the centripetal acceleration that it was like dominating the final answer. I didn't want that to happen. So when you draw your forces on the ramp, this is just like the classic ramp situation. You take your mg, your weight, and you break it down into components. You can figure out that the angle is a very small 0.91 degrees. And then you can use the angle. I can't find exactly where he did that, somewhere in here. But what you can do is you can use the angle to figure out what the velocity would have to be at that point. It's funny, like now I'm looking at it, I can't see where he figured out with that angle, but your acceleration ends up being g times the sine of theta. I think he did it right here. So force weight parallel is g times the sine of theta. So he said the acceleration is force weight parallel divided by the mass. So you get this acceleration is actually a tangential acceleration. We've never talked about that before, but it's a tangential acceleration. It's acceleration down the ramp, which is at a right angle to the radius. So therefore, it's not a centripetal acceleration. Then you can use that and you can figure out the velocity, which is identical to that because I think I said it was after 1 second. He said v equals a times t. So the velocity at that moment, that instantaneous centripetal acceleration is 0.1215. When you put these two together as a vector sum, and he actually drew this vector sum incorrectly, this should go here. But those two together produce an acceleration that's not directed toward the center. It's actually at an angle somewhat toward the center and somewhat straight down the ramp, and that's 0.19775 meters per second squared. That's the value of the acceleration. I'll take a little pause and I'll let you take a look at, I just like formatted this a little differently so I could write out my solution, but I'll let you take a look at this perseverance problem, which was Intro to Work and Energy. There are two ways to solve this roller coaster problem, and here's the thing. In this box and in this box, I want you to write something that's kind of like unique. I don't know if I want to say I want you to write something unique. I want you to write what you think the major principle is that I used. What principle, what general rule did I use here? Now, whenever I see a roller coaster, I think energy because I don't have to worry about angles. I can just think what kind of energy does it have in the beginning? What kind of energy does it have at the end? In the beginning, it has both kinetic and potential. Then it has kinetic and potential at the end. Beginning being right here, end being right there. Now the trick is, we'll get to. The trick is we're not talking about, it needs like a little bit of extra velocity to make it around this without leaving the track, and we'll talk about that later. So you can easily solve to get that velocity. I checked off every quantity we knew, and then I put a little question mark because we didn't know the velocity. The centripetal force, at that point, you have two forces going down, normal force and weight. Therefore, the centripetal force is the sum of those two. Therefore, the centripetal force, the normal force, when you plug in the numbers and solve for Fn, you get 3,120. So I'm wondering what general rule. Now, if you write the word centripetal force, that's not a rule. If you write down the concept of centripetal force, then that begs the question, well, what is this concept that you're using, right? If you write down a law, I want to know, like, what is the law? Like, say the actual law. Okay. All right, right here, this is the second question. And now we're starting from rest. So there's no velocity in the beginning. There is a velocity at the end, which is, again, at this point. And just for fun, I plugged in the values. I plugged in just the variables without the values. The normal force, here's the trick. This is the part you got to slow down. You really got to think about. The normal force at this point is 0. We did the demonstration with the marble around the hoop. The marble, you could hear the marble contacting the hoop the whole time. You could hear a temporary break in the sound of the marble on the track if we keep going slower and slower and slower. So it just barely makes that. The normal force gets less and less and less till it becomes virtually 0. Now, if you don't like the idea that the marble is like leaving the track because that's not safe for the roller coaster, fine. Say that the roller coaster is barely touching the track, but with 1,000th of a Newton or a billionth of a Newton. Does that even exist? So when you plug in here with the weight being the only centripetal force, you get V squared equals RG, V equals the square root of RG, plug, plug, plug. You get all these things cancel out when you solve for H, including the G, and you get 2.5 times the radius is the height. It just seems, it's a satisfying result. It seems kind of so arbitrary. 6.25 meters, the answer to the perseverance problem. Now the facet of physics here is perseverance itself, and you could say that that applies to any discipline. But also, the facet is this idea of having a perspective on problem solving, where every time you see a problem, you have to think about what is the domain? What is this? Within what realm do I even deal with this problem? Is it an acceleration problem? Is it a kinematics problem? Is it a free fall problem? Is it an electricity problem? Is this circular motion? Like, you have to be able to categorize and have the physics intuition to identify what your approach is going to be. And the worst case scenario is you're wrong and you kind of have to backtrack. That happens to me. Sometimes you don't know and you have to backtrack. This has been Physics from Afar.